Yeah, so this isn't too difficult. How does the centripetal acceleration of a car around a curve compare with that due to gravity? What is the magnitude of the centripetal acceleration of a car following a curve of radius 500 meters at a speed of 25 meters per second? Compare the acceleration with that due to gravity for this fairly gentle curve taken at highway speed. So, and then what is the magnitude of the centripetal acceleration? So that's AC equals question mark of a car traveling on a bank following a curve, something like that. Of a car following a curve of radius 500 meters. So that's what that looks like. A curve radius 500 meters at a speed. So his velocity 25 meters per second. Compare the acceleration with that due to gravity. And then acceleration compared to versus gravity. Acceleration compared to gravity. Ratio. Alright, so that's it. So and then we know our equations. Centripetal acceleration equals v squared over r. So that's why they put the v squared at 25 meters per second squared. R, which is 500 meters. So that's where we get that. What's the units? Meter squared over second squared. We get meters per second squared, which makes sense. It's an acceleration, so acceleration is in meters per second squared, so that makes sense. And it says compare it with the acceleration due to gravity. So and then she's saying my acceleration due to gravity. Alright, centripetal acceleration compared to the gravitational acceleration. You just put those over each other. 1.25 meters per second squared over 9.8 meters per second squared. So that's why we get that 0.128 of gravity. So if you just see this 0.128 of gravity, you know it's just saying it's 0.128 of gravity. That's like that roller coaster, that ride that I just showed y'all, that simulation. When they say G force, they'll say like 2 G's, 4 G's, 6 G's, whatever. That's just two times greater than the gravitational force, 2 G's. So if you hear about like rocket ships,
you found the speed of gravity?
Right, yeah. The force of gravity. Not so much, I don't really say the speed of gravity. But yeah, the force of gravity. Like the G-force in a rocket. In a rocket, the G-force is the thrust per unit mass, or the thrust to weight ratio multiplied by G. What it feels like. Astronauts experience intense G-forces when a rocket blasts off. So looks like 6G or more. The space shuttle experienced more than 3G on liftoff. When they coming back, it's about 6Gs. So I imagine I gotta control, like press some type of button or something, and we're going at 6 times the force of gravity.
Wow.
Yeah, so you know, you gotta be real fit. You gotta be able to lift 6 times the amount you would lift. You know, normally we could do this, but now imagine gravity 6 times actually.
Oh my God.
You know, so that's what that's saying. So boom, boom, boom. And then it's always the centripetal acceleration is always forcing inward. It always wants to bring you in. Centripetal wants to bring you in. Because you constantly have to turn the tire.
Think about center with centripetal. Like going to the center.
There we go, that's perfect. Because and then if not, then I'm constantly gonna be going outside of the circle. And that's the centrifugal force. So my velocity may be going at a straight, it is going straight, but centripetal acceleration brings you in. So that's what that's saying. My velocity is going straight out, but centripetal acceleration wants to bring me in. So me turning my tires is what's creating my centripetal acceleration to go inside of the circle. That's why you need good tires as you're out here, because it has to do with that friction.
What is it? What you call it? I don't know nothing about cars. The outside tires, the tread line, that's something that takes up with friction.
Yeah. So and then I could put this is my AC. Alright, so anyway. So that's that, and then
I have to skip out. An appointment.
no, you can't go to Delta right now.
No, I got another appointment.
Unless you get us some free plane tickets.
Yeah, I could, you know. Well, Delta, you might go to talk to Elise.
Or
What are you looking at?
Southwest.
Southwest.
Yeah.
Southwest?
Southwest is even better. Shoot.
Right.
I don't know about that right now. They trying to displace everybody.
But
Yeah, I think I might move to Houston or Nashville or something. I'll see y'all
All
Tuesday.
right, have a good one.
take care.
Tuesday the 8th, ain't it?
Yes. Yeah, because the
I
first.
won't be here Tuesday. I got court.
Oh, okay. Well, good luck.
Good luck. It's gonna go great.
Yeah,
Everything they asked.
that's what's up. That's good. So, how big is the centripetal acceleration of an ultra centrifuge? So that's even greater. Spin 7.5 times 10 to the 4 revolutions per minute. So that's a lot, right? 7.5 times 10 to the 4. How much is that?
That's 10,000.
Well, how how many times? Yeah, you put 4 zeros on the one.
Yeah, so 7.5
Move it
times
for
10 to the 4
4 times.
equals 7.5. We need 1, 2, 3, 4. 0, 0, 0.
75,000.
75,000
Ooh, look at that.
revolutions per minute.
Per minute, that's crazy.
That's a lot of
That is a
revolutions.
lot.
Dang, per minute?
And the ultra, but that's the ultra centrifuge right there. That's crazy.
Determine the ratio of this accelerate. So, and then they give us a radius. Calculate the centripetal acceleration of a point 7.5 centimeters from the axis. So, one thing you got centimeters here. The other thing you got the minutes rather than seconds. So you gotta take that into account because R is given. You can use the second expression in the equation.
I wish it was a smart board. I think it's just the way the big banner is just like a newer
Right.
thing. Every time I look at it, I just like, let me show them.
Yeah, it does look 4K, like it looks high quality.
Yeah, such a really good. They did a good one with this.
Yeah, Epson makes good products, but yeah, smartboard would be pretty nice. The term stands for revolutions per minute. So we know that by converting this to radians per second, we obtain the angular velocity. Because the R is given, we should use the second expression in the equation. And then centripetal acceleration equals R omega. What's omega? So that's when we're changing radians per second. So to convert revolutions per minute to radians per second, we use the fact that 1 revolution is 2 pi radians and 1 minute is 60 seconds. So that's saying omega equals 7.5 times 10 to the 4. It's revolutions per minute right now. I want to change it to radians per second.
So don't that just make it like 2 pi radian every 60 seconds?
Yeah. Yeah, 2 pi radian. 2 pi radian is 1 revolution. And 1 minute equals 60 seconds.
Just once you cross multiply. Or no?
Yeah.
So, but 2 pi, that wasn't that. That's 120. What is that? 120 pi radian every hour? But that, no, we trying to get this seconds, so.
So now I have to divide by the 60.
Okay.
So it's already solved for us. So 78.54 radians per second. Now the centripetal acceleration is given by the second expression, which is R omega squared. So that's omega. So our question is,
Oh, it was basically 75,000 revolutions over many times. Right here. Like, 'cause we had already changed it, so. I'm just saying to make it easier. Like, that don't have to be right there, you know, it's 75,000 pounds.
yeah, because omega's in radians per second instead of revolutions per minute. So, and then converting 7.5 centimeters to meters, substitute in known values. So, and then we see acceleration, centripetal acceleration is just the r omega squared, So we just got omega and the radius. 7.5 centimeters, so 100 value plus 2, 1, 2. So it should be 0.07 meters, yep. 0.075 meters times omega squared, so the 7854 squared. So apparently that gives us that 4.63 times 10 to the 6 meters per second squared. So now we know our acceleration, our centripetal acceleration, but it just asks us to do a ratio in gravity. Whenever they say do a ratio, that's just dividing the other, just dividing by it. So it's just saying, what is this amount compared to gravity? So we're just doing a centripetal acceleration divided by gravity. So that's where we get this 4.63 times 10 to the 6 meters per second squared divided by 9.8 meters per second squared. So that's where we get that. So now it's saying that 4.72 times 10 to the 5, that centripetal acceleration is way greater than gravity. Right? That's 4.72, 1, 2, 3, 4, 5, boom, boom, boom. 472,000 meters per second squared greater. It's no wonder that such high centrifuges are called ultra centrifuges. So that's an ultra centrifuge. Involved greatly decrease the time needed to cause the sedimentation of blood cells or other materials. So like you were saying, you just want to put those components apart when you're doing the biology, when y'all are doing that, what did you say, capillary
yeah, like
analyzation.
looking at a capillary stick sample.
Yeah, whatever that means. Something about blood.
Yeah.
Yeah.
They prick baby fingers. No, we did this at the plasma center. You have to take their blood so we can see their plasma and see if their iron is low or eating too
So
much
when it
sugar.
spins around, it's breaking up different
whatever
elements.
blood.
Okay. Wow. Yeah, that's pretty cool. Of course, a net external force is needed to cause any acceleration, just as Newton proposed in the second law of motion. So a net external force is needed to cause a centripetal acceleration. We would consider that was the same thing that we did before when the ladybug was just running around in a circle. So I'm gonna just get through this, and because this is pretty much the same thing. It's just centripetal force. So that way when we come back, they won't be too far behind. 222.
We on force now?
Yeah, so this is chapter 6. So we have centripetal force. Any force or combination of forces can cause a centripetal or radial acceleration. Just a few examples are the tension in the rope on a tether ball,
Yeah.
the force of Earth's gravity on the moon, friction between roller skates and a rink floor, a banked roadways, force on a car, and forces on the tube of a spinning centrifuge. And by the way, by the end of this section, we're going to look at calculating coefficient of friction on a car tire, calculating ideal speed and angle of a car on a turn. So that's why I wanted to bring up that friction earlier, just to kind of give you all a little heads up that we're going to be doing some friction. Any net force causing uniform circular motion is called a centripetal force. Direction of a centripetal force is always toward the center of curvature, the same as the direction of centripetal acceleration. According to Newton's second law of motion, net force is mass times acceleration. Net force equals mass times acceleration. For uniform circular motion, the acceleration is the centripetal acceleration. Thus, the magnitude of centripetal force is pretty much the same thing. Magnitude centripetal force equals mass times centripetal acceleration. And then we know that centripetal acceleration is v squared over r, or r omega squared. We get the two expressions for centripetal force. So you could either use m times v squared over r, or m times r omega squared. So when I'm in atmospheric science class, we were doing centripetal and something else called centrifugal forces, which is going to be coming up next, the Coriolis force. So I actually learned about the Coriolis force because if you're like tornadoes or something, tornadoes are going to pull in a lot of that energy, and it's going to pull it in going toward the middle. You know, that's why they have that spinning cyclone that's like, it's like elongated, you know, it's real tight because it wants to pull it into the middle, wants to bring all that. And like, because there's a low pressure, because most storms happen with low pressures because air wants to go into that point. So that's and then due to centripetal acceleration, it's not just gonna all just come in and then be able to like go straight. So it turns. So because I mean, it makes sense if everything went in, then it would like just hit each other or something. You know, just, like, fuck up. But that's not what happens in the natural world. The world is spinning, the tornadoes, the storms, pressure, like everything has a cyclonic nature, a spinning nature. Almost everything has a spinning nature. So that's why that's right after forces Newton's laws of motion. Because, of course, yeah, you can go straight, but after that straight line, that next one is spinning, it's turning. So it's very important. All right, so you may use whichever expression, and then it's just talking about radius. Get mv squared over the centripetal force. So that's the next equation. So that was that and that. This implies that for a given mass and velocity, a large centripetal force causes a small radius of curvature, that is a tight curve. A large centripetal force causes a small radius of curvature. Yeah, because if I turn my wheels in more to be a greater centripetal force, if I turn my wheels in more, then I'm cutting this radius. So that makes sense. F the small f equals centripetal. Is parallel to acceleration. Parallel to centripetal acceleration. So we know centripetal acceleration goes straight in since F equals ma. So it's directly proportionate to centripetal acceleration. What coefficient of friction do car tires need on a flat curve? So calculate the centripetal force exerted on a 900 kilogram car that negotiates a 500 meter radius curve at 25 meters per second. Assuming an unbanked curve, find the minimum static coefficient of friction between the tires and the road, static friction being the reason that keeps the car from slipping. Calculate the centripetal force.
So it would be in Newton.
Yeah, so yeah, that's the SI unit for forces is the Newton. kg times meters per second squared. Yeah, that's the SI unit for F. F equals ma. Because if you look at what F is mass times acceleration. Mass is a kilogram, acceleration is a meter per second squared. So the Newton, that's what a Newton is. A Newton is kg times meters per second squared. Yeah. So and then it's saying mv squared over r. So that's pretty much makes sense. Mass times velocity squared over 500, which was the radius that they gave us. So our centripetal force. So and then where did I get mv squared over r? We go up. It's mass. We know F equals ma. So and then it's mass times a, which acceleration for a centripetal acceleration is v squared over r, which is also r omega squared. So it has to do with the v squared over r. It's just like saying that I'm going around in a circle, and then I have the r, and then there's a v. So v. So it's saying the change in v over this time, delta v. Well, it's not really the change in v, but it has to do with the delta s. Delta s, that's the change of delta s. The change of my rate, my angular arc angle. Delta s is the change of the arc angle. But you then delta s over delta t is the acceleration. Delta s it's kind of like my position